All right, we're going to continue some examples from chapter 11. All right, so let's say that there's a radio station that has a frequency of 103.7 megahertz. What we want to know is what the wavelength is. All right, so what is lambda? Lambda is how many meters? All right, so the way that we do that, of course, is with this equation. The speed of light in a vacuum is equal to the wavelength times the frequency. All right, so, and of course, the speed of light in a vacuum, c, is 3 times 10 to the 8th meters per second. All right, so that'll give us an answer. Remember, hertz is also the same as 1 over seconds, or it's actually cycles per second. But all right, so the only thing that we really have to change here is the mega. The metric prefix mega means times 10 to the 6th. So that's the only thing. All right, so let's rearrange this equation right here and solve for lambda, right? So lambda is going to equal, so it's the speed of light divided by the frequency. We divide both sides by f, so it's going to be c divided by f. All right, so again, the speed of light is 3 times 10 to the 8th in a vacuum, of course, meters per second, divided by, all right, so it's going to be 103.7, and mega means times 10 to the 6th. And hertz and 1 over seconds are the same thing. So this and this cancel. All right, and so that'll give us an answer in meters. All right, so let's get out our calculator. All right, so here, let me move it over just a little bit. And so here we go. So 3 times 10 to the 8th divided by 103.7. And then, of course, it's megahertz, so it's times 10 to the 6th. So this is going to be the wavelength of this particular radio station in meters. So we'll round it to one place past the decimal. So it's going to be 2.9. So the wavelength turns out to be 2.9 meters. All right. So like I would ask you, round this to one place past the decimal. What's the wavelength in meters? So you'd type 2.9. All right. Let's do another example. All right. Let's do another Snell's law. So you have a beam of light coming in. This dotted line, I didn't draw it very well, but this dotted line represents the normal to the surface, and so this is supposed to be theta 1. So this is the incident ray, and then it's going to come out in some new material, and we're trying to figure out the index of refraction of that new material. So if we know what theta 1 is. So theta 1, N1 is 1. So that means that it's air, right? So let's say that theta 1 was, I don't know, how about 30 degrees, just to make our lives easy again. One thing I failed to mention in the last video, and I want to make sure that everybody's clear on this, make sure that your scientific calculator is in degree mode. All right, if you don't know how to do that, you have to hit function and you have to change it. Usually, like a TI, the Texas Instrument ones, they're usually set up in what are called radians, which are not degrees, and so you have to go down and change it to where it says degrees, from radian to degrees. All right, anyhow, let's say that theta 2. So this is like you did in lab, or if you haven't done the lab yet. This is what you do. All right, so let's say theta 2 is measured to be, I don't know, how about 24 degrees. All right, so theta 2 that's a degree sign. All right, and so what is this? This is going to be, so it's N1 times the sine of theta 1, so it's going to be the sine of 30 degrees, make sure your calculator's in degrees, is equal to N2 times the sine of theta 2, which is, in our case, 24. All right, so 24 degrees. All right, so here, that's what, and so this is what N2 is. and 2 is the sine of 30 degrees. 30 degrees divided by the sine of 24 degrees. And now you have to take the sine of each of those, and then I'll show you on the calculator. All right. So here's my scientific calculator. Let me clear that. All right. So for mine, it's these trig functions, and they're already in. It's already in degree mode. But again, if you have a Texas Instrument, and if you need help, I can show you how to do this. How to change it to degree mode. All right. So you do 30. Right. The 30 of the so this is how you always know your calculator's in degree mode. The sine of 30 degrees is always 0.5. All right. So we're going to take the sine, right? I just hit this trigonometry thing, and then it's going to take the sine of 30. Right. So the answer is 0.5. Right. So it's 0.5, and then we divide that by the sine of 24. Right. So divided by 24 sine. All right, and so we say equals. All right, so this is the index of refraction. So the index of refraction of this material, N2, whatever it happens to be, is let's round it to 2 places past the decimal, 1.23. All right, so that, remember, the index of refraction is a unitless number, so you'd put 1.23. All right, so that's the index of refraction. Oops, sorry. Goodness, didn't mean to do that. All right, so here's our next problem. Let's say and this is the deepest red that the human eye can actually see. So let's say you had some red light, and you measured the wavelength to be 700 nanometers. And again, that's the deepest red that the human eye can see. What's the frequency of that red light? Right, so we have an equation that we need to use. Of course, it's the speed of light, c, is equal to the wavelength times the frequency. All right. Now the wavelength has to be in meters. In this particular case, the wavelength is in nanometers. But if you know your metric prefixes, nano means times 10 to the minus ninth. All right. So you can just rearrange this and solve for f. All right. So we're going to solve for f. Divide both sides by lambda, and you're done. All right, so there it is. All right, so let me rewrite this. All right, so F is equal to the speed of light, c, divided by lambda. All right, and again, c is, it's always the same. It's the speed of light in a vacuum is 3 times 10 to the 8th meters per second. Notice this time the meters are going to cancel. And so it's going to be 700. And of course, remember, it's nano, so it's times 10 to the minus ninth. All right, and that's meters. All right, so notice this meters cancels this meters, and that leaves us with 1 over seconds, and 1 over seconds is exactly what hertz. That's what hertz are. All right, so we got to do this problem. So let me break out my scientific calculator, move it over a little bit. All right, let's clear that. All right, so it's 3 times 10 to the 8th, 3 exp 8. All right, divided by 700, and then exp to the minus ninth. All right, so 3 times 10 to the 8th divided by 700 times 10 to the minus ninth equals. All right, so let's see what this is. All right, there's my decimal point right here. So I'm going to put it in scientific notation. I'm going to round it to 2 places past the decimal. So it looks like it's going to be 4.2. Since it's an 8, and the next digit is 5. It's going to be 4.29. All right. So then we got to figure out how many decimals. All right. So this calculator is nice because it gives you little commas. So this is 1, 2, 3. There's 6, there's 9, there's 12, and then 2 more would be 14. So 4.29 times 10 to the 14th. All right, so that's hertz. So let me rewrite that. So 4.29 So we're rounding it 2 places past the decimal, times 10 to the 14th. And of course, the units are hertz, which is the same as 1 over seconds. All right, very nice. There's a problem. All right, so here's another example. Suppose the speed of light in some material was measured to be 2.96 times 10 to the 8th meters per second. We want to find the index of refraction. All right, so keep in mind the index of refraction n is equal to the speed of light in a vacuum divided by the speed of light in the material. So this is 3 times 10 to the 8th meters per second. Of course, that's the speed of light in a vacuum divided by 2.96 times 10 to the 8th meters per second. All right, and notice the meters per second cancel, of course, and also the times 10 to the 8th cancels. You could put it in your, as long as you put them both in, but those two cancel because you're just multiplying by the same factor in the numerator and the denominator. So, let's see, where's my calculator? Here it is. Move it off to the side. All right, so here, let's clear it. All right, so it's just going to be, I'm going to show you that it's going to work out in both ways. So it's 3 divided by 2.96 equals. All right, so this, that's pretty small. I didn't mean it to be that small. So this would be, some type of gas, let's say, it's passing through. So it's slightly, it has so I'd round this to 2 places past the decimal. All right, so this would be the index of refraction for this would be 1.01. All right, so here let's look at the number again. Yeah, so just to show you that this does work. I mean, you can try it yourself. So it's here 3 times 10 to the 8th. Remember, that's if you put that in there, you just have to divide by 2.96 times 10 to the 8th. And you get the same thing. So the index of refraction would be 1.01. Here, let's do a slightly different one. I don't like, I didn't mean the index of refraction to be that small. All right, so let's say the speed of light was, I'm just making this one up. Let's say it's 2.63 times 10 to the 8th. All right, meters per second, of course. What is the index of refraction? So again, n is equal to question mark. N is 3 times 10 to the 8th. The speed of light in a vacuum, that's an m, meters per second divided by 2.63 times 10 to the 8th meters per second. And of course, the meters per second cancel, the times 10 to the 8th cancels. And so it's just 3 divided by 2.63. So what is that? I don't know. Let's check. Here we go. So 3 divided by 2.63. All right, so that's a better one. We'll round it to 2 places past the decimal. So that would be an index of refraction of 1.14. Right, so that would be 1.14. All right, so and remember, you could be asked, if you're given that index of refraction, solve for v, right? So you would just rearrange the equation. Remember, the equation is just c divided by v, right? And so if you rearrange that and solve for v, v is going to equal c divided by n. All right, so you can just take the speed of light divided by 1.14, and you'll get approximately 2.63 times 10 to the 8th. All right, those are some good examples for chapter 11. Very nice.